So let's take an example, look at some examples doing the second fundamental theorem of calculus. All right, so take a look at what we have here. We're looking to evaluate the derivative with respect to x of the integral from 0 to x of t cosine t dt. So what we notice is that we have the derivative directly in this variable here of this function t cosine t dt. So this is pretty much a straightforward substitution. Basically what we're going to get is we're going to get t cosine t in now the x variable. So we're just going to replace t with x, because the fundamental theorem says that we should basically get this function back in this new variable. So we just get x cosine x. Yes, it's that straightforward. It's that simple in this case. Nothing more to do. We do not want to try and integrate this and then differentiate it. The whole point of this theorem is to not do that. We don't right now have a way of doing that because we can't integrate this easily. That was something that will come in Calc 2. But the point is we don't want to do that here. Okay. So what if we have some capital F of x that is the integral from 3 to x squared t cosine t dt, and we're asked to find the derivative? Well, it's really a similar problem. If we're asked to find the derivative of capital F, then we're finding the derivative of the integral 3 to x squared t cosine t dt. All right. Now, the difference here is that this isn't simply just this variable here. It's x squared. But that was this other version here. This basically says that what we're going to do is we're still going to rewrite the inside function in this new variable, which is a function, but then we have to multiply by a chain rule derivative. So it's still going to be now x squared cosine of x squared, and then we have to multiply by the derivative of what was up here, x squared. So we get x squared cosine of x squared times 2x, or in other words 2x cubed cosine of x squared. Okay, so the difference was that instead of just having x up here, we had x squared. So that meant that it wasn't just a simple substitution, a change of variable from t cosine t. We did the substitution using x squared, but then we also had to take the derivative of what was on top here and multiply that at the end. Chain rule. Okay. Let's take a look at this one here. All right. So similar thing, we have this function and we want to take the derivative, so we'll set it back up like before as the derivative of the integral from sine x to 2 of radical t ln t dt. Okay, so everything looks okay except we have one issue. Look at where the constant is and where the function is. We're used to doing these the other way around. For the fundamental theorem, we do need the constant at the bottom. We have to be going from the constant at the bottom to x or some function of x. All right, so what do? That's not a big deal, because we know that if you want to switch the limits of integration, you just put a minus. So it's negative integral 2 to sine x radical t ln t dt. Okay, so what do we get? Well, again, we just have a negative there that we can take out. So we have this derivative. It's not x, it's sine x. So that just means sine x is going in for t, and then we need to append it with the multiplication of the chain rule factor. All right, so what we get is we get negative square root sine x ln sine x times the derivative of sine x. All right, so we get negative square root of sine x ln sine x times the derivative of sine x is cosine x. So that's it. There is our end result. Remember, in none of these are we actually doing the integration and then doing the differentiation. We're doing it all at once, and that's the beauty of the second fundamental theorem of calculus.